At this point, we've seen a bunch of different tests to tell whether or not a series converges or diverges. And the question is, how do you know which test to use when you're faced with a particular problem? And so I want to go through a couple examples of how you might choose which test is appropriate. And so the first test that we talked about was the nth term test, which, as a reminder, just said if you have a sequence of numbers and they don't go to zero, then your series definitely diverges. And so this test is sort of a sanity check, and it's the first one that you might try if you're pretty sure that a series obviously diverges. And so some examples that might be relevant here are if you have the sum of n, for example, or the sum of e to the 1 over n, or the sum of arctangent of n. And so the point is that for every one of these sequences right here, if I just look at the limit of n as n goes to infinity, that's infinity. And so this series can't possibly converge. If I look at e to the 1 over n, that tends towards 1. Or arctangent of n tends up to pi over 2, and so none of these could be convergent series. For the next one, the integral test, we saw that this would allow you to compare an integral to a corresponding series. And the time that you would want to use this is if you have a series and you think, I could do the integral of this. And so some examples might be if you had something that looks like 1 over x times ln of x. And the reason why that might be helpful is because you would know that you could use a u substitution here. If I'm talking about a series, though, then really the series would have looked like an n times an ln n. But the idea is that you just want to think about what happens if I replace the n with an x. Is that an easy integral to do? And also, is this a positive decreasing function? If so, then I'm good to go. A direct comparison test, on the other hand, is if there's something that if you just got rid of it and made an inequality, then you would know how to handle it. And so an example might be if you had the series 1 over n to the 4th plus 16. And so this series right here, the plus 16 is only making the series smaller overall. And so it would be easier to just drop it. And so we already know that 1 over n to the 4th plus 16 is just less than 1 over n to the 4th. And that one already converges by the p-test. Another type of example where the direct comparison test is essential to use is whenever you have a term that oscillates. And so, for example, if I had the sum of 5 plus sine of n over n, then I can compare this to either 4 over n or 6 over n, depending on which one's going to be more convenient. In this case, it would be better to compare it to 4 over n because 4 over n diverges, and so therefore this one, which is at least as big, has to diverge as well. The limit comparison test is when you want to find something about the leading terms of your series. And so this would be when you have a whole bunch of junk in the numerator and a whole bunch of junk in the denominator. And you know that most of the junk doesn't matter and you just want to reduce it to the leading terms here. Then that limit comparison test is going to be the tool that'll help you do that. Let's look at a couple examples to see how we might pick which rule to use. And so for this example here, 1 over ln of n, there are a couple options here. It is the case that we could try the integral test and try and integrate 1 over the natural log of x. But that integral is also not going to be one that's particularly easy to do. And so while that technique would work, it's maybe not as convenient as another test. The other test that might be more appropriate here is that ln of n is a very slow growing function. And so 1 over ln of n is a very big fraction overall. And so I know that 1 over the natural log of n is going to be even bigger than 1 over n, which is already a positive sequence. And so that means that 1 over ln of n diverges by direct comparison. And just to make sure that all of the details are filled in, that's because 1 over n diverges by the p-test, where p in this case would just be equal to 1. Okay, and for this other example right here, Again, this might be a positive decreasing function, and so you could definitely use the integral test again in this case. And in this case, you would have to use partial fractions then in order to evaluate the integral. But again, that's going to be a lot of work, and so it would work, but it's too complicated. And so really what I'd like to do is try and get rid of some of the garbage in the numerator and the denominator to make this easier. And so here I can see that the leading term in the numerator is going to be this 3n, and the leading term in the denominator is going to happen when I multiply these n's together and get n cubed. And so really I can tell that overall the behavior of this is going to be a 3n over n cubed, or roughly 3 over n squared. And so this should converge by some combination of the p-test and then something else that can help me compare it. And so in this case, I'd probably want to use the limit comparison test. And then what I'd want to limit compare it to is 3n over n cubed. And if you do that, you'll see that the limit of the ratio is 1, and so they must do the same thing.